In the second case, if y happens to be a vertex VP, then when you delete it, you are going to end up with as many disjoint subtrees as you would have edges incident at VP. In this example, you would end up with three disjoint subtrees. One of them is this one, the second one is this one, and one of them is that one. Now, if any one of these subtrees, let's call these, say, P1, P2, P3. If P1 happens to have a total weight which is greater than half the total weight of the entire tree, which means that its weight is greater than P2 and P3's total weight. So equivalently, if WP1 is greater than W of P2 plus W of P3, then what would you conclude? Then you would conclude that there is that all the optimum solutions to the problem are contained in P1. You would conclude that. The proof would be similar, except that you have to work it out now using P1 and the union of P2 and P3, or the rest of the subtrees. Okay. So this is quite straightforward, even though the proof may actually require some labor. Even though the ideas are simple, just working it out or writing it down may take some effort. But when you work out proofs, I want you to be very careful with the rules of the game. Proofs are proofs as long as you write them out correctly. If you change the idea or if you change the structure along the way, everything is gone. It doesn't matter how good an idea you might have for your proof. Okay? So it's a matter of writing it correctly. So that's why sometimes, well, actually a lot of times, I'm going to prove things here. And when I prove things, please make sure you observe some of the details of how things are actually being written down. Okay, that's important. All right, now I'm not going to prove this, but this is straightforward because, again, of the similar arguments we could raise for this one. But here's what I'm going to say. So suppose you have a point y, which is either an interior point or a vertex point, and let t1 up to tk, where k is either 2 or larger than 2. Let these tj's be the disjoint subtrees, which you would get when you delete y from t. And here's the solution. then Y is an absolute median if and only if something about these subtrees is true. What is that thing? Here. No, they don't have to be equal. Yes, okay. In what way? So WTJ, the total weight associated with... Good, yes. This should be true for every subtree 1 up to k. So if any of these subtrees has weight no larger than half the total weight, then Y must be the point that optimizes the problem. It's an absolute median. Because if one of them is the other way around, actually, then you know that all optimum points must be in that particular TJ, in which case Y cannot qualify as an optimum. Okay? So you require that, but this is an if and only if. So whenever Y is an optimum, this should be true, and whenever this is true, then Y should be an optimum. So at home, you might want to work out a proof for that. Okay? That's a true statement. It's not something you're going to find in the literature. Nevertheless, it's true because I can easily prove that, and you should be able to also prove that because you've got the appropriate insights by now. Okay? Well, let's not do that. You just work out a separate proof for this, starting from scratch or fresh, okay, with a fresh mind. Okay, so I'm going to stop discussing the median problem here, and I'm going to continue with center problems now. Incidentally, in that theorem, if Y is a vertex, of course, when Y is deleted, then that vertex is in none of these subtrees, which means that its weight is not included in the total weight of any of these subtrees. Okay, that's sort of important. Whereas in the case of an interior point, you have only 2 subtrees. So in that special case, we're talking about both subtrees being less than or equal to half the total weight, which means that they have to be equal. Somebody, I think it was Ataberk, who mentioned that they must be equal. Well, it's true only for the special case of Y being an interior point. Does everybody see that? In that case, you're going to have 2 inequalities for either subtree. And of course, those 2 inequalities will imply that they have to be equal. You can work that out. Okay? So an interior point is optimum for the absolute median problem if and only if, or only if. Well, actually, for the 3-network case, it's an if and only if. Both subtrees have the same total weight. Okay? They are perfectly balanced. Of course, such theorems are useful for performing sensitivity analysis on weights. So if you have a current optimum relative to a given set of weights, and if some of the weights change, then you know how the optimum shifts from the current point to somewhere else, okay? Just by looking at subtree weights. So suppose again you have a embedded network N with vertex set V, H set E, and you're trying to minimize f of x, where f of x is defined by the maximum weighted distance between x and vertex Vi. The maximum is over all vertices. Okay? If you have a point x bar which solves the problem, it's called an absolute center. I defined that earlier. In that case, the value of the objective function at that point, at the optimizing point, will give you a number which we call the one radius. It's called, or I will refer to it as R1, okay? The one radius. Why is it one? Because there's only one facility under consideration. If you had P facilities, it would be called the P radius, okay? But that we will see later. So, this can be again solved by restricting your attention to edge problems. Where the edge problem associated with edge, say, VP, VQ is simply the minimization of the same objective function over all points inside or in the edge, VP, VQ. So, the problem on the entire network can be solved by solving the edge-restricted problem, identifying edge-restricted minimum each case, and then of all the edge-restricted minima, you just choose the best one, the one that supplies the smallest value of f. Okay? You may have alternate solutions sometimes. Now, the edge-restricted problem can be easily solved. And the first solution method is proposed by Hakimi in the paper he wrote in 1964, the seminal paper that actually caused the network location domain to develop from that point on. So the graphical solution is, again, relying on the investigation of these two-piece linear functions. This is a two-piece linear function due to some vertex Vi. So if this is my Vp, this is my Vq, then this is the weighted distance associated with some vertex I. Okay? Actually, normally you have +1 or -1 as slopes, but when you multiply with the weight, you end up with that sort of slope. Then you may have another one, which may be a straight line, for example. That might be, for example, Wj, I different from j. You may also have, say, a function that may go like this. associated with, say, k. And when you look at the functions like this, you've got normally n of them. All you're doing is assume you've got only 3 of them under consideration. Suppose 1, 2, and 3. Then to define f of x, you're looking at the maximum of them at every point x. So the maximizing function is this one. Okay? The cross-hatchet portion of the functions, that defines the f function. In this case, n is equal to 3, so it's like that. Okay? This is just for demonstration purposes. All right, so once you find the maximum function, how do you find the minimizing point? It's simple. You investigate the endpoints. The endpoints may qualify as a possible minimum. In this case, actually, one endpoint is a minimum. Or you would investigate points of this sort where one of the functions is coming with a decreasing slope and continues, or the other one goes with an increasing slope. You want to investigate intersection points of that sort. Such an intersection point is not useful for you because it cannot be an optimizing point, because you have an increasing slope here and decreasing slope here, which means that, for example, here, over here, if you're at this point, if you move slightly to the right or slightly to the left, in either case, you get worse. You get increased in your objective function value. Whereas here, if you move to the right, you get worse. But if you move to the left, you get better. So it cannot be a local minimum, okay? Because there are points within a small neighborhood of such a point, such that a little move to the new point would give you a better objective value. All right, so you want to focus on intersection points of that sort. Let's make it an edge optimum, because you may have alternate optima. An edge optimum occurs at either an endpoint of the edge or at an intersection point where the slopes are oppositely signed. That's the main intuition here. This is where this, how you could solve this. Hakimi actually solved the problem. He solved an example problem by simply investigating breakpoints in this particular way by inspection. He just eyed them. Okay. Later on, of course, you can actually develop numerical methods to find these intersection points in appropriate order. Let me give you an example here. That's what it means, yeah. Oppositely signed means the sign in one direction is the opposite of the other one. Oh, I see what you're saying. Okay, okay. Yes, okay. Where the slopes are oppositely signed. Let's change it then. Yes, you're right. We need to differentiate between such a point and such a point. I see. Good. Those are not intersection points. Yes. Actually, they could be intersection points if you have something like this, for example. So, but nevertheless, you know the meaning we have in mind, okay? So I'm not going to be picky about it. All right, here's the example. It's a simple network, and I'm going to assume all weights are 1. Now the distance matrix can be computed, and it will give you the following. Okay, that's the distance matrix based on shortest path lengths between pairs of vertices. And let's investigate the f function on the edge V3, V4. This edge in the middle. Now, at V3, the distance to V1 is 12, and the weight is 12. So you begin at value 12 for vertex V1, and you start increasing with a slope of 1. And then at midpoint here, 7, okay? The shortest path from the points inside the edge to V1 switches from this endpoint to the other endpoint. At the midpoint, there are two shortest paths, one going through V3, the other one going through V4. Does everybody see that? So, at the midpoint here, you switch and start going down like that. Okay? Or you would continue like this, but it would no longer be shortest path length anymore. Okay? Is everybody following what I'm doing? I see some questioning eyes. Is everybody with me? Okay. So that's my G1. What is G1? Gi by definition, alpha is the length of the subarc from the endpoint VP or V3 in this case. So it's the minimum of 2 values. One is alpha plus the distance from 3 to I. The other one is 14 minus alpha plus the distance from 4 to I. At alpha equals 7, this is where the minimum changes from one to the other. Okay? Because this one is 12 in our case, this one is also 12, so that the switch occurs at 7. Okay? All right, that's my G1. What is my G2? G2 begins with a distance of 10, which is a little bit lower. It goes, well, actually, it goes all the way through V3. In other words, the minimum is always the first one for number 2 vertex. So it goes like this. And finally, it ends at 24 here. Okay? So that's G2. Number 3, G3. It begins at 0 and goes like this with a slope of +1. Ends at how much? 40. The next one, V4. It begins at 14 and decreases down to 0. That's my G4. And what is G5? G5 is the opposite of G2. So it will begin at 24 here. And it will go down to 10 somewhere here. Okay? That's the sort of thing you get. Of course, if you have many vertices, this would be very messy. Nevertheless, you do these things on a computer. Okay? And your f function happens to be this one. And by inspection, I have 2 local minimum. And the distance happens to be how much? How do you find that distance? In other words, how do you find how much this distance is? This is 7 here. The local minimum occurs at the point where 12 plus alpha, which is this one, intersects 24 minus alpha, which is that one. Yeah, that's G5. Okay. So the first intersection occurs at 12 plus alpha, intersecting 24 minus alpha. And when you solve for that, you get alpha equals 6. So there's one minimum at that point. The other one occurs at 10 plus alpha, which is this guy, G2, intersecting 24 minus alpha, right? Or is it 26 minus alpha? Why is that? Okay. Yeah, that's 26. Okay. All right. 26 minus alpha. That gives you alpha equals, how much is that? 2 alpha equals 16, so that's 8. Okay. Okay. Let me give you some additional properties of the center problem. By the way, if you had the vertex restricted center problem, how would you solve it? In that case, X is restricted to vertex locations, so all you have to do is you take the distance matrix, you multiply each column with the appropriate weights, if your weights are different. You multiply each column with those, and then for each row, so you get a new matrix with the weights multiplying the columns, and then in the new matrix you inspect each row and you pick the maximum. So out of the row maxima, you find the one that gives you the smallest. Okay, you may end up with alternate edges, alternate vertices. But back to the absolute center problem, there are some other properties we may actually identify here. So we're talking about f of x being the maximum of wi dx vi. This time I'm going to add a constant term ai. I'll make it a little bit more general. That's called an addend. Now, what's the meaning of addend? First of all, you used to have a linear function with no addend. In other words, all addends were 0. Now you still have a linear function in the distance with some constant added to it. The meaning of this is the following. If you have a network such as this one, and if you're locating, for example, say an ambulance, the ambulance will be located somewhere, okay, at X, for example. And you want to get to the vertices as quickly as possible, meaning you want to minimize the maximum distance to the vertices, weighted distance to the vertices. Now, if this is vertex vi, normally you get there, for example, going through a shortest path, say that one. That's your distance times x vi. But then once you get to the vertex, you need to take the victim or the patient to a closest hospital. Now the closest hospital might be somewhere here. And there's a fixed distance here to get from that VI to the closest hospital. Of course, there may be more than one hospital all over the place. We're not doing anything with respect to the hospitals. Nevertheless, once you get to the point of service or point where the service is needed, just getting there is not enough. Then you have to take your guy to the nearest hospital. So that AI is the distance to a nearest hospital in this interpretation. Of course, these AIs can be a priori computed by pre-processing the data. Just assume you're at vertex VI and compute the distance to a closest hospital. In the case of a fire station, you may interpret this in a different way. In that case, you would get again to the point of service in time, say, proportionate to Wi dx Vi. Once you get there, there may be a setup time to start firefighting. You may have to position your fire trucks, etc. It might take some time. And depending on Vi, the physical surrounding at Vi, you might have to spend more time at certain vertices and less time at certain other vertices. So you might want to differentiate the setup time using these add-ons. So anyway, you can certainly find other interpretations as well, but that's the problem we're going to look at. Now, the first property I'm going to give you is that there exists a minimum of the function f defined in that manner on n. This is, of course, obvious when you draw pictures, but nevertheless, sometimes you have to be careful with these things. And the reason why this is true is because the function dxvi is continuous function of x for each vertex vi. So each term in the maximum is a continuous function, which means that f of x is a, well, the maximum of continuous functions is a continuous function on the entire network. And since n is a compact set, so a continuous function f on a compact set n has a minimum. It attains a minimum. Again, those of you who are coming to this class without having had any metric space knowledge from before, don't worry too much about this. It's nevertheless at the graduate level, sometimes you need to worry about these things. All right, what's a compact set again? A closed and bounded set, yes, in our case. Okay? But in general, a compact set is a set that has a finite cover. That's the general definition, but which could be a little bit more general than just being bounded and closed. Okay. I'm going to define a certain number here, which you are going to see oftentimes in the rest of the semester whenever we deal with center type problems. That number is defined as follows. It's the total distance, or the distance between vertices I and j, plus ai over wi, plus aj over wj, the entire thing divided by sum of the reciprocal weights, 1 over wi plus 1 over wj. This is how I prefer to use this number. Nevertheless, typically you would see this number in a little bit different clothing in the literature. It will look like, I didn't even write it down, but how people write it is usually they multiply both the upper side and the lower side with wi times wj, in which case you end up with dij times wi times wj plus, what do you get here? wj ai plus you get wi aj, right? Divided by wi plus, or wj plus wi, so wi plus wj. This is usually how you would see it. It's the same thing. Okay, this is for every I, j pair between 1 and n. When I equals j, what does that give you? The distance becomes 0. You have ai over wi twice, and then you have 1 over wi twice, which means what do you get? ai. You just get ai. Right? Okay, yeah. All right. Let's define W associated with the network to be the maximum of these numbers. Okay, these are a priori computable. You just compute them and you pick the maximum value. And here's the next property, which you might want to work at home to prove. property 2. W of n, called the diameter of the network, is a lower bound on the function f. So f of x is always bounded below by this number. I'm going to give you the proof next time because we're out of time now. Okay. So much for today.